Let's talk about the conditional. This video is going to be a fair bit longer than my other videos on the logical connectives because the conditional is a bit of a tricky logical connective. In English, it comes in a lot of different variations, and the way that it evaluates in logic is a little bit weird at first. And there are like a bunch of caveats as to how this thing works and so on and so forth. So I want to dedicate some proper time to understanding this. Okay, so let's just go ahead and start off with the basics, right? So the conditional is just an if-then statement, right? So we use conditionals all the time in English, right? So if so-and-so is at the party, then I'm not going to go. Or if so-and-so is there, then I am going to go, right? And what you're doing is listing out a condition, right? Some condition by which you will do something or something will happen, right? So if the moon were made of cheese, then, I don't know, some weird funky physics stuff would happen. So this thing is all over natural language. But the thing is, it doesn't always present itself as an if-then. So I'm going to write down some variations, but bear in mind, there are many more than what I can actually fit on this board. There are many ways of expressing these if-then relations. So the most popular one, I'll use the letters P and Q, right, in order to represent atomic statements. So if P, then Q, right? That's the most popular one. That's the one that you're going to come across the most. P only if Q. This is where things get confusing because P only if Q expresses the exact same thing as if P then Q. And I'll explain why a little bit later on. You'll also have assuming that P Q or given P Q, and so on and so forth, right? So this sort of assuming that, given that, so on and so forth. There's a lot of language. Here's another one that might be surprising, right? All P, R, Q can be represented as a conditional statement because all this is saying is if something is P, then it is Q. You don't have to memorize that, and in fact, in most formal logic courses, you're mostly just going to have to deal with these two, right? And that's why I want to pay special attention to them. Okay, so let's talk about the anatomy of a conditional statement, because this is going to be super important. So I'm going to erase these. And let's discuss, I'll just write a particular conditional down. So let's go ahead and say something like, if I'm hungry, then I'm angry, right? Which seems perfectly descriptive. Okay, so this is a conditional, and the pieces of the conditional have names. And I want to cover those names and talk about why these things are called what they're called. So first and foremost, this bit here is what's known as the antecedent. And this is what's known as the consequent. You will see this terminology a lot in formal and informal logic courses. So I think that the terminology is actually relatively straightforward, right? It's the antecedent, the thing that comes before, right? It comes right after the if, it comes before the then. That's your antecedent. Just memorize it, right? There's no real importance behind doing anything more than just memorizing it, right? And then the consequent is just the thing that's supposed to follow from the antecedent, right? So given that I'm hungry, the consequence of that will be that I am angry. However, these two parts of the conditional are also known by other names that it's more important to bear in mind. So this first thing here, this antecedent, is what's known as the sufficient condition. And this consequent is what's known as the necessary condition. And there is a reason for that. So let's consider this let's assume for the sake of argument that this conditional is true, right? So if I'm hungry, then I'm angry. The reason this is called the sufficient condition is because according to what this conditional expresses, me being hungry is enough for me to be angry. It's sufficient, right? It suffices. Given that this is the case, you can expect that, so again, assuming that this is true, with certainty that I am going to be angry. Right? And in fact, If I'm hungry and not angry, then it turns out that the conditional is false, right? So given a true conditional, this condition will be sufficient for me being angry. Let me give you another example that actually might have been a better one. If I'm 10 feet tall, then I'm over 6 feet tall. Being 10 feet tall is sufficient for being over 6 feet tall. By itself, it's enough, right? If I'm 10 feet tall, that guarantees that I will be over 6 feet tall. Okay, so why is this one called the necessary condition, right? The reason it's called that is because me being angry is necessary, according to this conditional, for me being hungry. This does not mean that if I'm angry, then I'm hungry. That's not right. However, were I to fail to be angry, if I am not upset, then you know with certainty that I must not be hungry. So it's required for me being hungry, but it's not sufficient. It's not enough, right? It's just one of the requirements. Now, why is it necessary? Again, assuming that this conditional is true. Well, if I weren't angry, right, it can't be that I'm hungry, because if I were hungry, I would be angry, right? That's what this thing expresses. Let's use the 6 feet tall and 10 feet tall thing again, right? So if I'm 10 feet tall, then I'm over 6 feet tall. Being over 6 feet tall is necessary for me being 10 feet tall. If I'm not over 6 feet tall, I don't have a chance in hell of being 10 feet tall, right? That would be absolutely bad. It would be wrong, right? So this is the necessary condition precisely because it's required for the antecedent, right? But the mere fact that I meet this condition does not tell me whether the antecedent is true. Failing to meet this condition would tell me that the antecedent must not be the case, okay? So these two things are related in this very important way, right? The antecedent is sufficient for the consequent is necessary for the antecedent. Just to give one more example. If it's raining, then it's cloudy. That's absolutely true, right? You can't have rain without clouds somewhere because that's where rain comes from, right? So if it's raining, then it's cloudy. Rain is sufficient for cloudiness, right? If there's rain, then there must be some clouds. It being cloudy is not sufficient for rain, right? The mere fact that there are clouds does not entail that it's going to be raining. For instance, if you live in Seattle, a lot of clouds, not necessarily always raining, although it rains fairly frequently, right? However, a lack of clouds guarantees a lack of rain, right? So you need clouds for raininess. This is necessary for it to be raining. If it's not cloudy, you won't get any rain. But it being cloudy doesn't tell you that it is rain. Okay, then the last thing that I want to talk about here was the only if stuff, right? So I said that this is equivalent. It's raining only if it's cloudy. Notice that these are equivalent because the word only here is just picking out that this is a necessary condition, right? That's what only means. So it's raining only when it's cloudy, which just means were it to fail to be cloudy, then it would not be raining. Okay, I know that that can get tricky, so here's just something to bear in mind. If you have a hard time sometimes wrapping your head around this stuff, that's okay. Just memorize that if P then Q is equivalent to P only if Q. Just memorize that. And with enough practice, I promise that this stuff will start to settle in. Okay, so that's the anatomy of the conditional. Now let's talk about how the conditional works. And I'm going to do things a little differently in this video. I'm going to start with the truth table because things are going to get just a little bit strange. Okay, let's erase all this stuff. And let's write the truth table. So P, Q, P arrow Q, true, true, false, false, true, false, true, false. If you don't know how to set up a truth table, I recommend watching my video on truth tables. Watching my video on how to set up truth tables, because there I talk about why this is the arrangement of truth values and how many you need to write and so on and so forth. Okay, so I'm going to write down the truth values first, and then I'll explain them. So I've found it helpful to start by giving examples of how these truth values can actually evaluate this way with natural language conditionals, bearing in mind that there's a caveat coming up. Okay, This might look weird at first. The first row seems fine, right? If P is true and Q is true, then P implies Q should be true, right? And the second one seems fine too, right? So, if P is true and Q is false, then it seems like something went wrong. These two rows are the ones that sometimes trip people up. Why on earth would it be the case that if P is false and Q is true, then that comes out to be true, and if P is false and Q is false, then that comes out to be true? The first thing that I want to show you is that this arrangement here does happen in natural language, right? We see that all the time, right? So take as an example, right? If I'm 10 feet tall, then I'm over 4 feet tall. Notice, I am not 10 feet tall, right? I wouldn't want that. That sounds like a curse. So I'm not 10 feet tall. That's false. I am over 4 feet tall. That's true. Notice that conditional is absolutely true. If I'm 10 feet tall, then I'm over 4 feet tall. That's correct, right? So in natural language, you get conditionals like this all the time, where the antecedent is false and the consequent is true, and it still evaluates the truth. Just as well, you get conditionals where both are false. For instance, if I'm 10 feet tall, then I'm over 8 feet tall, right? I'm not 10 feet tall, and I'm not over 8 feet tall, but nonetheless, that conditional comes out to be true. Okay, here's the caveat. I said that only to show that happens sometimes, right? So, but conditionals don't really work that way. So notice, here's another conditional where both of these are false, right? If Paris is in France, sorry, that one's true. If Paris is in Germany, then the moon is made of cheese. That's just not true, right? And this would go ahead and evaluate it to true. Whether the moon is made of cheese has nothing to do with where Paris is located. So why this? Why do we end up with this bizarre series of truth values? And I'm going to tell you something that I wish I had been told when I first learned about how the conditional gets evaluated here. You might notice that in your textbook, and your professors will do this as well, this is called the material conditional. Here's what this means. This is not the natural language conditional. In fact, one of the shortcomings of statement logic is that we don't have an adequate representation of the natural language conditional. The logical system is just not strong enough to give us that. So do not treat this as a natural language if-then. That is not what this thing is. In fact, just pretend that this arrow means nothing at all and that these are the truth values that are assigned to it. Trust me, that will allow you to pass your classes without worrying too much about the semantic content of this. Okay, but I don't want to just leave it there, because I can imagine that it might be a little frustrating to then wonder, okay, well, if this isn't what we actually mean, then what's the point, right? Why do we have this? And I do have a satisfying answer for that one. Remember what the purpose of a formal system is. A formal system is just trying to capture inferences, right? So we're trying to represent the inferential connections of natural language. And the most important thing when it comes to representing those connections is that our arguments be truth-preserving, right? We need to make sure that when we construct these formalized arguments, what they do is capture the truth preservation of natural language reasoning. And that's what this does. If you translate every natural language conditional to this material conditional, you will never be led astray. You'll never have an argument that's valid in English that turns out to be invalid in sentence logic. And that's the thing that you want to avoid. You want to make sure that every valid argument in sentence logic is a valid argument in English, right? And vice versa. This is what's known as syntactic versus semantic entailment. You want to make sure that every syntactic entailment, those are the formal things, matches the semantic entailments of natural language, right? That's the meaning stuff that we understand. So, just one more time for the sake of repetition, just to drive the point home, right? This thing is not the natural language if-then. So don't get bogged down trying to understand what's going on with these two rows. The only thing that matters here is this row. That's the row that guarantees that nothing goes wrong. Because One thing that's absolutely true about natural language conditionals that this material conditional captures is that any and every natural language conditional with a true antecedent and a false consequent will be false every time. And this thing will not allow that to break, right? This guarantees that if you have a conditional that starts with true and ends with false, it spits out false. That's what we need this to do. That's the row that matters the most. These two, if we just let them evaluate to true, no problem, right? We're never going to run into any issues when we're constructing our proofs or anything like that. So this is merely a pragmatic representation. We do have formal systems that try to capture what the conditional is saying, especially in modal logic. If you don't know what that is, that's okay. Just want to let you know that we do try to fix this, right, in more advanced systems. But for this basic introductory system, just treat this as a sort of useful tool, right? Something that just lets you make your truth tables and build your proofs and whatnot. And you can rest easy at night knowing that the system's not going to do anything it's not supposed to, right? It's going to guarantee that if you start with truth, you end with truth. And that's what this is doing. You start with truth, you end with truth, great, right? And if you start with truth and end with false, then you're going to get false out the other end. Is there anything else that matters here? Yes, the formal definition. So before I let you go, let me give you the formal definition that captures what it is that this truth table is supposed to be doing. So, a conditional is false if and only if its antecedent is true and its consequent is false. Otherwise, it's true. This definition will give you this truth table every single time, right? It tells you that a conditional is false when this antecedent is true and this consequent is false. Otherwise, every other row is true. Hopefully that clears up the conditional for you. I know that this one can be a little bit tricky. Let me know in the comments if there's anything that I could do to make it clearer. I'll engage with you in the comments if you have any questions, anything I could do to help you out. Stick around. I'll be uploading more videos. I think I have only the biconditional left to do, and then I'll start uploading videos on actual truth tables and how it is that we use them and whatnot. So I'll see you around.